Putnam here with the vector thingy. Now, before I get into what the vector thingy can do for us, a couple of things, of course, as we know, in physics and in math, one of the basic concepts we do in the first part of the year are vector and scalar quantities. Now, a scalar quantity referring to just magnitude or just a number, and vector referring to a number, magnitude, and a direction. So vectors are really important in every kind of problem that we do, whether it's a force problem, a motion problem, momentum problem, whatever it happens to be, in math and physics class. And so it's generally we do the problems on paper and maybe a simulation here or there, but for the most part, kids are doing it on paper and they're not actually able to manipulate and see what visually happens with vectors. Whereas this device can actually do that. Now, for basic vector knowledge, most of the vectors, of course, that you might do in, say, 8th grade or a lower level physics would be vectors that are actually at right angles to each other. We call that concurrent vectors, acting on the same point. And the vector thingy here is able to show that very nicely. As we move those two vectors back and forth, and if we set it actually at 90 degrees, and you can see, of course, on here that we can set that angle to 90 degrees, okay? That would be the angle between the vectors here, right? We can see what we call the resultant, what results from those two vectors, right? And of course, we can use the Pythagorean theorem to calculate those as well. Now, one of the things that's interesting in physics, and it's kind of difficult for students to understand, is what happens when the angle between these two vectors increases. If the angle between them increases, right, what happens to the resultant? And a lot of students don't think about what really happens, but the vector thingy is able to actually visualize this. You can see that the resultant actually decreases, as opposed to when the angle between two vectors decreases. Again, in this case, let's say at 40 degrees right here, what happens to the resultant? You can see the resultant grows. So this is a fantastic little device that you can use with any of your problems that you might have, that you might write out yourself. You can use it with lab. You can have it on a tabletop to help you visualize what it is. And not only does it have the angle between the concurrent vectors, but it also shows you what we call the supplementary angles. When you're ready to solve vectors, okay, if it's not at a right angle, okay, if it is at a right angle vector, we can use the Pythagorean theorem. If it's not a right angle vector, for example, greater than 90 or less than 90, right? Then what happens is we will have to use the law of cosines to solve that. And this vector thingy is able to do that. So this can be used, again, for high school physics. Would it be used for AP physics? Possibly in a low-level AP physics, something of that nature, but mostly for high school level physics and math class. And I really like this because students can actually physically solve if they want to, not just in a general way, but these vectors are actually measured out, okay? We have one that's 220 millimeters and one that is 300 millimeters. So they can physically do the problem, which I will do in just a moment, okay, in a second video. So that's kind of the reason that I really like this vector thingy. Again, as you increase the angle between them or you decrease the angle between them, you're able to visually and conceptually see what's going on with those vectors, right? By the way, the vector thingy is actually very, very precise. And its accuracy is excellent, basically under 5% error. I've seen this where it's in less than 1% error when you're actually calculating with real numbers. And so that's what's really nice about this particular thing. You can also use this for review, for a quiz or a test, which would be great, and each student can have this at their desktop. What I would like to show now is what you would actually do as a sample for your class. I'm going to do a right angle vector, concurrent, and I'll do a concurrent vector at a non-right angle, just to show you how this might work. And the vector thingy is excellent at doing this. This is all included on the teacher's answer sheet manual. Again, you can use your own. You can use any vector problems that you want, and the vector thingy really adapts to it nicely, okay? Or you can use the ones we've included here with your answer key, okay? So let me just show you one right now. This would be one on the vector, using the vector thingy with the two vectors of 300 millimeters and 220 millimeters. And if it was at 90 degrees, you would draw it like this. Now again, I don't have a grid here, so I'm going to just draw this to a kind of a conceptual scale, okay? And so this would be 300 millimeters, and this would be 220 millimeters, okay? And when you want to solve this, you want to find the resultant of those two. So what you'll do is, using the parallelogram method, you can move either the 220 or the 300. I'll happen to move the 220, so that makes that 220 millimeters over here. And we have made a parallelogram, and now, of course, we can find the resultant from where we began to where we end up, and we want to find the resultant. That's what we want to find right there, okay? So you would set this up like this. You would say c squared equals a squared plus b squared, okay? C squared would be your resultant, okay? A squared, again, it wouldn't matter which side is A. We'll call this side A. We'll call this side B. So A is 220 millimeters squared plus B, which would be 300 millimeters squared. And this would come out to be C squared equals 48,400 plus 9,000, check that, 90,000. And C squared would equal 138,400. And of course, to solve this, you would want to square root that. And C will come out to be, I'm not worried about significant digits here, 372.0 millimeters. This would be what we call the resultant. The resultant would be this, okay? If you actually did this with your vector thingy, if you actually solved this, you would find this would be, percent error would be very, very small percent error here in actually using the vector thingy to do that at 90 degrees. You would set this right at 90 degrees, okay? Just to show you how this works. And you would have your 220 and your 300, just like I've drawn here, okay? Exactly like I've drawn here. And you can measure this from the point here where they are concurrent to this point here, and you will find that it will come out to be 372.0 millimeters, give or take a small percentage error, okay? Again, it's extremely small percentage error. What we're going to do is we're actually going to use the vector thingy for an angle here that is not 90 degrees. So to show you how this works, I'm going to put the angle here between the two of them at about 40 degrees. So we're going to put it at 40 degrees between them. Okay, this will be at 40 degrees here. And you can see what happens to the resultant, right? But again, I'm going to use these actual numbers that are written here on the vector thingy, and I'll draw it for you, okay? So basically, you would draw it like this. I'm going to use it, again, I'm going to draw it just like the vector thingy is here, okay? I'm going to make this 220 millimeters, and I'm going to make this one 300 millimeters, and the angle between them is 40 degrees, okay? Let's make sure you get that in there, 40 degrees, okay? And so, again, what would it look like? Well, this is what you would draw on paper, of course. You can move either one of these using the parallelogram method. So I'm going to move the 220 just because it can be consistent here. And we've made a parallelogram. So again, where's our resultant? From where we began to where we end up here, and that is our resultant. You can see the resultant gets much bigger. Again, using the vector thingy, as we decrease the angle between them, the resultant increases. And again, let's do the math here on this, okay? Just to show you how this works. Now again, we cannot use the Pythagorean theorem because now we have a non-right angled concurrent vectors. So what we need to have for this problem is we need to have the supplementary angle, which is really nice because the vector thingy does give that to students. if you're not sure. Again, these angles must add up to 180 degrees, so that supplementary angle is 140 degrees. And so you would set it up like this, okay? You would say c squared equals a squared plus b squared minus 2 times a times b times the cosine of c, using the law of cosines to solve for side c, which in this case would be the resultant, okay? So you would say c squared equals 220 squared plus 300 squared minus 2 times 220 times 300, and I'm just going to erase this right here so we can see a little bit better, okay, times the cosine of 140 degrees. And if you do that, of course, this is going to come out to be 489.4 millimeters. That would be side C, which would be our resultant, okay? And so, and again, the accuracy of the vector thingy is astounding because it comes out to be a very small percentage of error here on this. So, again, what would I use this for? Guys, this can be used for lab, can be used for review for a quiz, a test. You can use this on homework. We can have this on the lab tables. They can visually see one of the more common questions, by the way, that you see all the time on any state test, whether it's New York or other states, is they tend to ask you what happens as the angle increases between concurrent vectors, and what happens when the angle is decreased. And so they can visually see what happens as well. Again, a tool here that can be used to manipulate conceptually or quantitatively. You can actually do this. So it's a qualitative and a quantitative type of device.